So welcome you back to today's module. So what we were doing in last couple of lectures is we're trying to develop methodology to compare two or more estimators asymptotically, in the sense that sample size goes to infinity. The first approach we did in that direction was comparison in terms of asymptotic risk. And then we developed a few results which tell you how to compare two different estimators in terms of limiting risk. Then we realized that there is a disadvantage with limiting risk approaches, especially in situations where the movements may not exist. So if second movement do not exist under the square error loss function, risk does not exist. So the approach of limiting risk efficiency cannot be adopted in those situations. So then we said what one can do in such situations is, rather than looking for a limiting risk, one can look at the limiting asymptotic distribution. So normally what would happen is there exists a sequence Kn. So normally there will exist a sequence Kn such that Kn goes to infinity, and Kn times delta n minus g theta goes in distribution to normal 0 tau square theta, where tau theta is positive. So certainly this condition implies that delta n is consistent for g theta, because Kn is going to infinity, so 1 upon Kn goes to 0. So that means this multiplied by 1 by Kn goes in probability to 0, which is equivalent to saying that delta n minus g theta goes in probability to 0, which is equivalent to saying that delta n is consistent for g theta. So this certainly ensures that delta n is consistent for g theta. So what may happen is you try to look at this normalizing Kn for different sequences, and the one for which the convergence rate is better, or for which 1 upon Kn goes to 0 much faster, or Kn going to infinity much faster, that estimator should be preferred. So this is a scenario which is happening in many situations. Now in many situations what may happen is you're comparing sequences that root n delta n minus g theta. So normalizing constant is root n, is always going in distribution to normal 0 v theta. So you might have more than one estimators for which rate of convergence is 1 upon root n. So suppose you have two different estimators for which root of convergence is root n, then you compare their asymptotic variances. Whichever is smaller, that estimator should be preferred. But then the question arises, if you recall your last course, you could found a bound Kramer-Rao lower bound. So the question is, can we find a Kramer-Rao lower bound on v theta also? And the answer is yes. We said that v theta would always be greater than or equal to, under certain conditions, v theta would always be greater than or equal to g prime theta whole square by I theta, where I theta is the information contained in single observation, which is nothing but expected value of minus del square by del theta square log f theta x1, and which you also know is same as expected value of del by del theta log of f theta x1 whole square. So what this suggests, that means for any estimator for which root of rate of convergence is 1 upon root n, v theta would always be greater than or equal to this thing. So this suggested that I can talk about saying when do I say an estimator is asymptotically efficient? So I say an estimator is locally efficient if this equality is attained. So such estimator is called locally efficient estimator. Now when we did this result is under certain regularity conditions, which of course are satisfied in the case of exponential families, and those regularity conditions are basically that your PDF is twice differentiable, double derivative is bounded by a function which is integrable, and so on. But even under those conditions, it says that this inequality holds almost everywhere. That means the set of points where this inequality does not hold will have a Lebesgue measure 0. So what it suggests is that we might have few thetas where this inequality doesn't hold. But the set of all such thetas would have a Lebesgue measure 0. But more important to note is there could be some thetas where this inequality is not attained. To see such an example, let us look at x1, x2, xn are IID normal theta 1. So where such an inequality doesn't hold, the set of points theta where this inequality doesn't hold, we call such points as points of super efficiency. So x1, x2, xn are IID normal theta 1, theta belongs to capital theta, and my parameter space is whole R. Estimand is theta. It is exponential family, so all those regularity conditions are satisfied. One can look at that. So I first try to find out what is I theta. Expected value of minus del square by del theta square log of f theta x1. Now if you recall your last course, or you just even if you do a simple algebra, you see that in the normal case, the information contained in single observation is inversely proportional to the variance, and variance is 1, so which is 1. So I theta is 1. So what you know is x bar is MLE. It is also UMVE. You also know that root n x bar minus theta goes in distribution to, in fact, in this case it is an exact distribution, normal 0, 1. So V theta turns out to be 1. And what is G prime theta whole square by I theta? That is also 1, because G prime theta is 1, I theta is 1, so this is 1, which is same as V theta. So what does that mean? That V theta is always greater than or equal to 1, greater than or equal to G prime theta whole square by I theta, but in the case of x bar, the equality is attained. So this says that x bar is asymptotically efficient. Now what I'll do is I'll consider one example where again this inequality is attained almost everywhere, but then there are few thetas where this inequality is not attained. Of course, set of all those thetas would have a Lebesgue measure 0. So let us try to consider the following example. So for 0 less than or equal to a less than 1, let delta nx is same as x bar if mod of x bar is greater than or equal to 1 by n to power 1 by 4, and a times x bar mod of x bar is less than 1 upon n to power 1 by 4. So what I would show is delta nx also with this normalization root n delta nx minus theta goes to normal distribution. So let's try to see that. So let's try to see what is the probability that root n delta nx minus theta. The reason why I am considering that is because note that this differs from x bar in this set. And this set as n goes to infinity, because is it n to power 1 by 4 mod of x bar, that one can show that that probability is going to 0. So it looks like this should behave like a x bar only. One can easily see that. So this is same as I break it into two parts. using theorem of total probability, depending on whether mod of x bar is greater than or equal to 1 upon n to power 1 by 4 or mod of x bar is less than 1 upon n to power 4. So this is same as root n delta nx minus theta is less than or equal to x, mod of x bar is greater than or equal to 1 upon n to power 1 by 4 plus probability that root n delta nx minus theta is less than or equal to x, and mod of x bar is less than 1 upon n to power 1 by 4. So if I see over here, when mod of x bar is greater than or equal to 1 upon n to power 4, delta n is same as x bar. So I can replace here it by x bar. So let me do that. In this range, delta nx is same as x bar. So this condition imposes that delta n is same as x bar. And then this imposes that delta nx is same as ax bar. Good. So now what I do is I try to see what is the condition mod of x bar is greater than or equal to 1 upon n to power 4. So or mod of x bar is less than 1 upon n to power 4. So case first, theta is not equal to 0. Then you can get an intuitive feel of what would happen to n to power 1 by 4 mod of x bar. Now in this case, you know that x bar goes in probability to theta. So mod of x bar goes in probability to mod of x theta. So, and mod of theta would be positive because theta is not 0. So mod of theta is over here. So this says as n becomes large, probability that x bar would be in neighborhood of this, that probability would be 1. And probability that x bar would be outside any neighborhood of this would be 0. So when I say that probability that in this case mod of x bar is less than 1 upon n to power 1 by 4. Now note that when n is very large, 1 upon n to power 1 by 4 is going to 0. So this probability would be over here. Mod of x bar over here. And mod of theta is far away from that point. So this probability is going to be 0 as n goes to infinity. Because this is a heuristic argument, you can prove it exactly. So what is happening is I expect that mod of x bar would be in any neighborhood of mod of theta, however small that is. And probability that mod of x bar would be outside any neighborhood around mod of theta would be 0. What is happening when n is large, 1 upon n to power 1 by 4 is maybe far away from mod of theta. So probability that I can find a neighborhood such that x bar is outside that neighborhood of mod of theta. That is what this probability is talking about. So this has to go to 0 as n goes to infinity. Otherwise also you can do it. This is same as x bar lies between minus 1 by n to power 4, 1 upon n to power 4. You know that x bar is a normal theta 1 by n. You can write down exactly that probability and calculate it. But I have given you a heuristic argument. Okay, so what happens is this probability is going to 0. So probability that root n so that means as n goes to infinity, what happens to as n goes to infinity? As n goes to infinity, probability of this would be less than or equal to probability that mod of x bar is less than 1 upon n to power 4, because probability of A intersection B is less than or equal to probability of A. So this joint probability would be less than or equal to probability mod of x bar less than 1 upon n to power 1 by 4, and that is going to 0. So this less than or equal to something which is going to 0, so in limit this would also go to 0, because this is always non-negative. So in limit this probability would be same as this probability. So this is same as probability that limit n going to infinity, probability that root n x bar minus theta is less than or equal to x, and mod of x bar is greater than 1 upon n to the power 1 by 4. Now again, by the same logic, one can show that probability of this is going to 1, or probability of mod of x bar less than or equal to 1 upon n to the power 4 is 0. So probability root n x bar minus theta less than or equal to x is same as probability of this intersection this plus probability root n x bar minus theta less than or equal to x mod of x bar less than 1 by n to the power 4. The second probability is going to 0. So this probability would be same as probability that limit n going to infinity, because this probability is going to 1. If this probability is going to 1, then this probability would be same as limit n going to infinity, probability that root n x bar minus theta is less than or equal to x. And this, you know, in fact, in this case it is exact probability the same as phi of x. All right. If you want, you can write down this probability in two parts: probability root n x bar minus theta less than or equal to x, intersection x bar less than minus 1 upon n to the power 4, plus root n x bar minus theta less than or equal to x, x bar greater than 1 upon n to the power 4. You know the distribution of x bar, and you can find it out. But here I have just given you a direct argument, because this probability is going to 1. So if you have a probability of Bn intersection Cn, and probability of Cn goes to 1, then probability of Bn intersection Cn has to go to P of Bn, which is what is happening over here. Now let's look at case 2. Theta is equal to 0. Now in this case, by strong law of large numbers, you know that x bar goes in probability to 0. So that means probability that x bar is outside any interval of 0 is 0. So 0 is over here. You look at however small interval around 0, probability that x bar lies between minus epsilon, that is 0. So what would be probability that mod of x bar less than 1 upon n to the power 1 by 4? In this case, or in fact, you can consider just x bar less than 1 upon n to the power 4. Now, however small neighborhood you take around epsilon, you can always find n large enough so that 0, however small neighborhood you take, you can always find n large enough so that 1 upon n to the power 4, minus 1 upon n to the power 4 and 1 upon n to the power 4 is contained in this. And that would happen for every n greater than or equal to n naught. So you can always choose an epsilon so that probability that mod of x bar less than 1 upon n to the power 4, this probability 1 upon n to the power 1 by 4 is always less than epsilon. So this probability would always be greater than or equal to probability that mod of x bar is greater than epsilon. So what I have done is let epsilon greater than 0 be fixed. Then there exists a n naught, of course, which depends only on epsilon, such that 1 upon n to the power 1 by 4 is less than epsilon for all n greater than or equal to n naught. That is what I am doing. So I am choosing n large enough so that minus 1 upon n to the power 4 or 1 upon n to the power 4 is less than epsilon. So minus 1 upon n to the power 4 would be greater than minus epsilon. So this, and this happens for every n greater than or equal to n naught. Now if that is the case, then for every n greater than or equal to n naught, probability mod of x bar less than 1 upon n to the power 4 sorry, let me just see over here. So mod of x bar less than 1 upon n to the power 4. I want that this is going to 0. X bar, in fact, what we know is we know much more than this. So let me just write it down over here. In this case, what we know is root n x bar goes in distribution to normal 0, 1. So root n to power 1 by 4 x bar would be how much? N to power 1 by 4 would be nothing but I multiply and divide by root n, so it becomes root n. So 1 upon n to the power 1 by 4 root n x bar. This goes to 0, this goes in distribution to this thing, so this will go in probability to 0. So root n to the power 1 by 4 x bar will go in probability to 0. So in that case, what would be probability that mod of x bar is greater than or equal to 1 upon n to the power 4? This would be nothing but probability that n to the power 1 by 4 mod of n to the power 1 by 4 x bar is greater than or equal to 1. But since n to the power 1 by 4 x bar goes in probability to 0, so that probability that this would be greater than or equal to 1 would go to 0. So in this case, what happens? This probability goes to 0. So this limit would be same as this limit, and this would be finally same as probability that so this in this case probability that root n, I'm just everywhere putting theta is equal to 0, so delta n x minus 0 is less than or equal to x. In limit this would be limit of this and limit of this. This limit would go to 0 because probability A intersection B would be less than or equal to probability of this, but this is itself is going to 0. So this would be same as limit of this, but limit of this would be same as, by the argument same as in the last case, this would be same as probability that root n into ax bar is less than or equal to x. Now what is the distribution of root n x bar? Root n x bar is normal 0, 1. So this is same as phi of x by a. So what do you get? You get root n delta x minus theta. So in either case, your asymptotic distribution is normal, except that depending on theta is 0 or theta is 1, the variance gets changed. So what you get is root n delta nx minus theta goes in distribution to normal 0 v theta. And what is your v theta? V theta we have seen if theta is not equal to 0, this is 1. And when theta is 0, variance is, mean is 0, variance is a square. My a is between 0 to 1. So what is happening? You know that v theta is this, and what is a g prime theta whole square by I theta? This is 1. So v theta is not exactly equal to 1 because I can choose a suitably so that a square is bigger than 1 or less than 1. The way I have chosen a is between 0 to 1, so a square is less than 1. So in this case, this inequality is not satisfied at theta is equal to 0. So I can call the point theta is equal to 0 as point of super efficiency. So v theta is equal to g prime theta whole square by I theta is not satisfied at theta is equal to 0. So there is only one point where it is not satisfied, and you know that Lebesgue measure of a singleton is 0. So that means the conclusion of last theorem holds. That means the set where it may not hold would have a Lebesgue measure 0. So the set where it does not hold is a singleton 0, and the Lebesgue measure of a singleton is 0. So but there is a point where it does not hold. So this is a point of super efficiency. So this was an example to illustrate there could be a point of super efficiency where that condition is not satisfied. Now this result has a limited applicability in the sense here you can only compare two estimators for which the rate is 1 upon root n. Because this Kramer this bound which we have gotten, it is only for those estimators for which the rate at which the asymptotic distribution converges is 1 upon root n. Now in general, when you are comparing estimators, what you first do is you try to look at what are the rates at which the asymptotic distribution converges, centered around g theta. Now if the rates are same, then you would like to compare it through asymptotic variance. So I can talk about the concept of asymptotic relative efficiency here exactly the same way we talked about local limiting risk efficiency. So let me do over here. So what I do is first I fix the rate for one of the estimators. Let us say delta n1 is one estimator, and I fix rate for that. So that means suppose I know the rate for that. So that means I know that n to power alpha minus delta n1 minus g theta goes in distribution to normal 0 tau 1 square theta. I know that this has a rate n to power alpha when sample size n is taken from this, when delta n1 is based on a sample of size n. Now I try to look at what should be the sample size for delta 2 so that I get the same rate 1 upon n to power alpha. And then I compare the two sample sizes the way we did in the limiting risk efficiency case. So let me give the definition of asymptotic relative efficiency. We talked about limiting risk efficiency, which was talking about efficiency in terms of a limiting risk. When we talk about asymptotic relative efficiency, it is about talking efficiency in terms of asymptotic distribution. So what you have is you have estimators delta n1 and delta n2. So two sequence of estimators delta n1 and delta n2 for estimate g theta. So I know that for delta n1 the rate is n to power alpha. So suppose for some alpha greater than 0, delta n to power alpha delta n1 minus g theta goes in distribution to normal 0 tau square theta. And any sequence n prime, which is n prime of n going to infinity n to power alpha delta n prime. So let me write down delta n prime minus g theta. So for delta n2, I fix the rates same, I fix the variance also same, goes to the same. So that means to achieve the same rate and the same asymptotic variance, delta n1 requires a sample size n, whereas delta n2 requires a sample size n prime. So I define the asymptotic relative efficiency of delta 1 relative to delta 2. So relative efficiency, I also call sometimes this as ARE, is defined by so let me call that as E delta 1 delta 2 theta as limit n going to infinity. Now note that relative efficiency of delta 1 is smaller if its sample size is smaller. So that means it should be inversely proportional to the sample size. So that means numerator here sample size of delta 2 should come. So n prime n divided by n. Provided the limit exists and is independent of any sequence n prime such that this holds. So a justification of this is, or an interpretation of this is, that E delta 1 E delta 2 theta is half for every theta. Let us look at it. What does that mean? That means relative efficiency of delta 1 is half, less than 1. It says, in other words, that delta 1 would require twice sample size than that required by delta 2 to achieve the same efficiency or to achieve the same performance level. That is what the interpretation is. So what I'll do in the next module is I'll develop some easier methods to find out E delta 1, E delta 2. So that's all I have for this module. Next module, I would like to conclude this asymptotic relative efficiency. First, I'll do one result, and then I'll give an example. I'll consider an example to illustrate application of the given result. So that's all for this module. See you in the next module. Thank you very much.